This lesson is mainly review of a few concepts. Make sure you know the difference between linear and exponential before we go on to simple and compound interest. Start with linear growth. Linear growth is something that changes by the same amount each period. Okay, and there should be a line between these. Looks like this. Growing in a linear fashion. Linear is the adjective form of the word line, okay, and growing in a straight line. And we can see that for each year we go across, it's going up the same amount in the y-axis, okay, in this case in the value. General form of a linear function, hopefully this isn't news to anyone, is y equals mx plus c. Okay, where c is the initial amount. So in my graph on the right here, this initial amount would be 5,000. Okay, and m is the amount of change per period. So we can see here, each time I go up by 1 in time, I'm increasing the value by 200. So the formula for this one, for example, would be in the y equals mx plus c form, it'd be y equals 200 x plus 5,000. Okay, just be careful, even though this is the y-axis and this is the x-axis, we've labeled these as different variables. So this will actually end up being v equals 200t plus 5,000. Okay, hopefully you'll end up getting comfortable just going straight to this line, okay, without having to think in terms of y's and x's, because there's going to be heaps more letters coming up. Okay, so it's the idea of linear growth. M is the amount of change per period. So if something's increasing 10 per period, m equals 10. If it's decreasing by 50, say, each period, m would equal negative 50. Okay, so the sign in front of the number for m indicates whether it's positive growth or negative growth. Okay, we'll then have a look at exponential functions, which we should be pretty good at because we've looked at them just recently rather. Okay, it talks about changes by the same percentage each period. So each time I go up 1 hour, okay, I'm not going up the same amount. Okay, but what we'll find is I'm increasing it by the same percentage. So to this initial value, I'm going to multiply by some growth or decay factor. Okay, multiply by something. Here multiply by the same number. Here multiply by the same number. Here multiply by the same number. Okay, this is essentially a geometric series. Okay, but the difference between exponential functions and geometric series is our geometric series, we could only have t1, t2, t3, t4, etc. Whereas with exponential functions, this general form y equals k a to the x, this x value can be anything. So I can have, like, if I wanted to, I could have 1.276 as my time value. Okay, like t 1.276, okay, which I can't have in my general geometric series. Okay, so that's the general idea. We've got a general form of a exponential graph, y equals k a to the power x. K is the initial value. I can't even think what that initial value would be. Okay, I'm not going to try and write the formula for this one, a bit too hard to read off the graph. Okay, but A is the growth or decay factor. So if it's a growth factor, the A value will be greater than 1. If it's a decay factor, the A value will be less than 1. Okay. Basically the number we're multiplying by each time. So if I'm doubling something each period, A equals 2, tripling, A equals 3. If I'm going to increase it by 10% each period, I'm really finding 110% of the thing each time. Okay, it'll be 1.1. Increase by 1% each period. I'm really finding 101% each time, 1.01. Decreasing by 5% each period. Remember, this is all review. Finding 95% of it each time, 0.95. Halving it each period. Okay, so finding 50% of it each period, 0.5, and decreasing by 75% each period. Okay, finding 25% of it each time, so 0.25. Okay, so from here, I want you to have a go at these questions. I don't think they'll take you too long at all. Okay, so pause this and do them. All right, welcome back. The second part of this lesson is about actually determining the relationships, okay, whether it's linear or exponential between two variables. So I'll look at this first relationship, and I'm just having a look at the time. Each time I increase the time by 1, looking at what happens to the population. I think it's pretty clear that in each of these steps, we're subtracting 20 from the population. Okay, so we know that our m value, okay, what's happening after each time we increase the time or the x value by 1 is it's decreasing by 20. So my slope would be minus 20. My initial value is 200. So if I want to write this as a formula in the form y equals mx plus c, okay, this is my y, this is my x, so I'm going to use these proper letters straight up. My population is minus 20t plus 200. Okay, so you're just substituting in m into here, c into here, and using p and t instead of x and y. Now look at part B, see if it's linear or exponential. Okay, I'll test if it's linear. Okay, increasing by 50, increasing by 150. Okay, it's not linear. Okay, since it doesn't increase by the same amount each period. Okay, so that's no good. I can test for whether it's exponential, okay, just in the same way that we test whether something's a geometric series. So I'll do like t, the second term divided by the first term. So 150 on 100, 1.5. Test these other two, 300 on 150 equals 2. Okay, so it doesn't seem to be exponential either. Okay, so not exponential since not increased by the same percentage each period. Okay, so I just threw that one in there so that you don't think that everything's either linear or exponential. Some things just grow at a random rate. Okay, part C, we'll try and have a look what's going on here. Okay, is it linear or exponential? Okay, here I'm increasing by 1, here I'm increasing by 1.1. Okay, so it's not linear. Test whether it's exponential. 11 on 10 is 1.1. 12.1 on 11. I'll do a few of these. So realistically, you should be testing all of these. Okay, and I'll be a good demo and do that for you. Okay, so 12.1 on 11 is 1.1, cool. 13.31, 12.1 sounds good. And the last one, okay, it's pretty much 1.1. I think it's just a little bit of rounding in that last hourly wage. Okay, so I'm happy for all of these to be 1.1. Okay, so I'm going to state that this is an exponential function. Okay, where the k value, so the thing I'm multiplying by each time, is 1.1, which would be an increase of 10%. Okay, initial value, correction, an a value of 1.1. Initial value is 10, so my model, basic exponential model, is k(a to the power x). Okay, again, x and y. So w equals 10 times 1.1 to the power of t. Okay, get used to not using x's and y's all the time. Okay, for the final one, looks like a decay model. Quickly test whether it's linear. Going down by 10, down by 9, no good. Okay, not linear. I'll test successive terms to see if there's some exponential relationship. Okay, trying to be a good demo again. Yeah, 0.9, 81 on 90, 0.9 sounds good. 72.9, yeah, 0.9. Hey, they're all 0.9, sounds good. 0.9, 0.9, 0.9, 0.9. So it's an exponential function. My a value is 0.9. Which means it's decreasing by 10% each time. Initial value of 100. My model will be v equals my initial value 100 times the decay rate to the power of t. Okay, again, x's and y's here. Okay, get used to not having x's and y's all over the place. Alright, so that'll do from there. If you want to have a go at, say, question 3 and question 17 before you come to class, that'd be great. Okay, otherwise, come to class and have a go at these problems, especially these modeling problem-solving ones, so that you can get familiar with linear and exponential functions.